Hello everybody, welcome to this session on video analytics for football games. My name is Sven Degroote and I'm a machine learning engineer working at ML6. Very shortly going to cover ML6. So we are a consulting services company specialized in machine learning. We are a Google Cloud partner since 2014 and we mainly work together with customers to try to solve their toughest challenges. And one of these challenges is the use case I'm presenting today. So the use case I will talk to you today is about video analytics for football games. I want to introduce you to our customer. So our customer is an international player in the sports business. He is traditionally known for broadcasting big events on television, and he was looking for new business opportunities in the digital era. So he came to us with the following question, and I've tried to summarize it in one big sentence to catch the essence of the project context. But his or her question was mainly to, I'm going to say it once out loud. So design and create a platform that can handle auto production and broadcasting for up to hundreds of games per weekend with as little time delay as possible. And the boundary conditions that we had is that we had 3 months and we had 4 people to solve this. And we had to prove that this is something which would be feasible. So it's a very big sentence, and I'm going to take you through it in terms of what it means to system requirements, and then I'm going to translate that into how we actually solved it and introduce you the solution, basically. Okay. So first of all, I'm going to highlight the word auto production. So it means that starting from a raw video feed, we need to crunch through the data and visualize it in a way that it becomes attractable to watch, like showing where the players are, showing a mini-map. So this is the first part of the auto production, which I'm showing on this slide. So basically you want to detect all of the players and where the ball is at, because then you already have a sense of where the action is going, who is having the ball, etc., and you can start calculating metrics on top of that information. So this part, player and ball tracking, is typically something you do on a frame-by-frame basis. So looking at a single frame, you can draw the boxes around all of the players. So that's kind of straightforward if you have a good object detection model. So again, this can be detected frame by frame. So on this slide, I'm showing you a fictive timeline of a video, which is starting at 0 and then 1, 2, 3, 4, 5 seconds. If we are working at 10 frames per second, that means that within 1 second, we have to process all of those 10 frames individually and detect all of the players and the balls. The second part of the auto production equation is more related to events. So you don't want to see only just the players and the balls, and you want to see the minimap, but you also want to know, has the game started? Because the data that we're talking about is starting in advance of the game. So just imagine a team is just warming up, the video feed starts, but that's quite boring to watch. So we also had to predict when the game started so we can keep track of time and keep track of the scoreboard. So start of game is just a simple example, but very crucial for just your end user because he doesn't want to watch the warm-up, right? So, and then next to start of game, you have goal detection, but you also have fouls, free kicks, corner kicks, etc. But these are different in nature from the player and ball tracking because this is typically something you do on a sequence of frames. So if you want to see who made a foul against whom, or you want to see who scored a goal, or you want to detect a goal, it's very hard to do it on a single frame. Even for a human being, just looking at a single frame and try to detect if there's a goal, yes or no, sometimes it can be obvious, but providing a sequence of frames gives you more accuracy, it gives you more confidence. So this is a very important aspect in terms of data that we will need to work with windows of frames in order to predict a start of game, a foul, etc. So if you look again at the video timeline, this time we're making windows of all of the frames. So just imagine that we have a model which can predict start of game, but it needs to have a window of 3 seconds. So based on a 3 seconds window, we can decide or we can make a prediction if there was a start of game, yes or no, or if there was a goal, yes or no. But you see that this is very different in nature to start make a prediction out of this data. So typically events, we will need to group frames in windows and pass those windows onto our machine learning models to make an accurate prediction. So the first part was on the auto prediction part. The second part of the project context is more about infrastructure. So it's, in the sentence it says broadcasting for up to hundreds of games with as little time delay as possible. So just imagine Saturday afternoon, 3 p.m., a lot of leagues, a lot of games are starting, so your infrastructure needs to scale up to hundreds of games within 50 minutes, basically, and with as little time delay as possible. So the order of magnitude here is that we have an acceptable delay of 10 to 20 seconds. So that means that by the time the streaming is online, 10 seconds or 20 seconds later, we need to have a prediction of all of the facts of that video stream. So just trying to summarize again the problem statement so it's very clear for everybody what we're trying to solve. So on the left-hand side, you have the football field. There's a camera at one side of the field, which is recording a very wide video feed, and it's going to push that video stream into a URL on the cloud. And then the customer is basically expecting us to start from that HTTP live streaming and then just process the whole video feed and then just make it available in a player, so it's attractable to watch. And I'm going to show you just the raw video feed, just so you have some kind of feeling with what kind of data we're handling, and also why the raw data is not something you can just expose to your end user, because it's not really enjoyable to watch. So I'm going to I'm going to open up the video, and I hope it will not break, otherwise I'm going to get a small heart attack. Yes, okay, it's playing. Perfect. So this is the start of the video feed, and you can see that the players are just warming up. The width and height is about 4,000 width and 800 high in terms of pixel size. But you can see that this is not very enjoyable to watch because, yeah, of course they're warming up. But if I just open up another video, if I just fast forward to 27 minutes in the game is actually started, but you can see it's very hard to follow what's going on because the camera is at one side of the field. So if the ball is at the other side, everything becomes very small and it's not really enjoyable to watch, right? So the main challenge we were trying to solve is to make this into something which is watchable. So it's like zooming in where the action is happening. You can have a scoreboard, you can see what's the score, and just applying these first features to make it really something that's a product, or that can be a real nice product. Right, I'm going to go back to the presentation. So now that we have a brief understanding of what the challenges that we're trying to solve, I'm going to talk you to two parts of the solution. So the first part is mainly focused around what kinds of data did we train on and how did our machine learning models look like. And then the second part is more related to the backend system, and there we're going to deep dive into some code. So yes, let's get into it. So data. So we were promised to see or to have a lot of labels, but unfortunately, day one of the project, we were told that there were no or very little labels available. So this is a very typical challenge in machine learning that, yeah, obviously the labels make up your model, how strong it is, but sometimes you just have to be clever on how you go about the data if you have very little labels available, and I will show you how we solved it. But just to show you a bit of what kinds of videos we are talking about, you've already seen one, but this is just some just spot checks out of the data, and you can see that the spread is very wide. There's even a hockey field inside of it. So just to let you see that you need to be very careful of what kinds of data you're training on, because if you put garbage in, you will get garbage out, right? That also holds for machine learning. So you need to be very careful about that. Just to say that the data was very spread, and we had to be very careful on what data that we select for the model training. So very short, the data facts. So on player and ball tracking, you know, object detection models these days are very accurate. So we did not need actually any data for player tracking. But for ball tracking, we found that it was not accurate enough. So we had to label 700 frames additionally to make it accurate enough. So this was, I think, the kind of phases that we had after labeling about 700 frames. So it's not always a fun job, but it's part of the job, right? So the next thing was for start of game. What we did here is, if you have a very little amount of labels, you can just train a first model based on those labels, and then you can make predictions with that model that you just trained, and then this will give you hotspots for new events. So the model that you trained will give you true positives, so real start of games that it actually predicted right, but it will also give you a lot of wrong examples, but at least you don't need to go through a lot of data to get to those events. You kind of get hotspots by leveraging your model, and by this feedback loop you can basically label faster. So that's the trick, and and this is the way how we got up to 2,000 positive events. Then for goals, we also did not have any labels for that, so that was also a challenge on how we will get to those data points. And we kind of figured out that there are public APIs available, so you have a lot of leaks, and you can just consult public APIs to get indications of when goals happened. And we kind of used those as well as hotspots for our labelers, so they could just directly go to that hotspot and try to look around that window to see if there's an event, yes or no. But these kind of tricks really helped us speed up the labeling process, which was very necessary for us to work with it. So the models, player and ball tracking, so we kind of experimented with a lot of different models, pre-trained networks, of course, and we kind of noticed that YOLO V3, which is a well-known network, really had a very decent performance, and it already had player and ball classes. So it was already able to predict players and predict balls and put them in a separate class. And as I mentioned before, so we had to label a bit more to get really accurate on the ball tracking as well. And I will show you visualization between the difference of no extra labels and then the 700 extra labels that we added. You will see that the model is really performing differently. One of the challenges that we had to face is that the video is warped. So I'm going to show it to you. So if you look at the upper image, you can see that the lines of the football field, they are warped. So if you want to go from bounding boxes to real field coordinates, you need to do a transformation. So in the middle image, you can see that the frame is now dewarped to a way that the football lines, or the lines of the field, are now straight lines. So now you can actually calculate the field coordinates. Another challenge that comes along with this is that some models are so powerful that they actually detect all of the supporters at the other side of the field. So this is not something you want, of course. So you also need to will need to put in some logic that if the player box is outside of the football field lines, then you just discard that detection. And this is an example of the ball tracking with and without retraining. So you can see on the left-hand side, without the extra data, it's doing a fine job, but it kind of loses the ball between some frames. And on the right-hand side, you can see that it's much more stable. Then team detection, so it's not just sufficient to know where the players are at, you also need to classify them, to which team do they belong. So the initial idea that you have, or that you could have as a machine learning engineer, is to embed all of the player boxes with a convolutional neural network and just cluster them on embeddings, on a vector representation. But the issues that we faced here was that you will kind of get a added latency, because you need to send all of the bounding boxes through your network to get the embeddings. And we found that there was a big impact of the background. And also you need to rescale your crops so it fits with the size that your model is expecting. So a lot of challenges, but if you visualize it, it's kind of nice to see, and it gives you an idea of what we're actually doing. So you can see that here we're walking in our feature space. So by embedding, I mean that you literally vectorize a player and you put them in a three-dimensional space. And here you can see, if we zoom in on the red ones, sometimes there's also a white one. And that has to do with the background, which is playing an influence, but also there might be an arm of the other team's player, which is influencing the clustering. So you can see that it does a very well job, but it's not perfect. So an alternative idea was to subtract the background and then just cluster them on color. And I'm going to show you the video, because this was actually performing very well. Just to show you, and it also has a trail which is following the players along. So now you can see that it's actually doing a very good job at separating players from one team to another team. And it's also keeping track of the trail. You might notice that the trail will be less accurate if it's the other side of the field, right? Because it's further away and it gets harder to keep track of it. Just to mention that we had no decision about how many cameras we could use, just so you know. The setup was a given. We had thousands of videos, and that's what we had to work with, basically. So there was no way to add an extra camera on the other side of the field to compensate these kind of challenges. I'm going to go back to the presentation. So if we can subtract the background, we can do a very good job at team detection. But one sad thing is that for background subtraction, you need to keep a state, right? You need to know the former frames that you've seen so you can subtract the background. And the problem with big data engines or distributed data frameworks is that it's kind of hard to keep a state across your workers. And for us, that was not possible yet with the tools, but I will come back to it later on, which tools we used for that. But basically, this was not an option. So one alternative idea was just to remove the green color range and cluster them in the HS spectrum, which is an alternative for the RGB spectrum, but it was doing a better job for differentiating different colors. So basically, we filter out the green color range out of the player boxes, and we map them. We map all of the pixels onto the HS spectrum, and then we can cluster. If we get those centroids, we can know to which teams they belong. The next thing we had to also solve was start of game. So what kind of data do you feed a model to predict start of game? The first setup we came up with was, on one hand side, optical flow. Optical flow is basically the delta between two frames. So it has the notion of motion between two frames. So this is one input feature. The other input feature is inception model. So it's also an embedding on the visual representation of the image. And you can see that there's a list of frames because we have, as I still told you before, those are windows. So we're actually sending, with 3-second windows, we're sending 30 frames of optical flow and we're sending 30 frames of inception features. And then the model takes in those two lists of 30 frames, or two input features basically, and it will predict some number between 0 and 1, right? You could also argue that why don't you use player and ball coordinates? Of course, yes, it's very logical, but you must know that at the time that we started, we first had to solve the player and ball coordinates, and only when you solve that, you can start using it downstream for other models. So it's a very valuable feature, but you first need to get it stable before you can use it downstream, because if your feature is not doing a good job, or if your player and ball tracking model is not doing a good job, then your downstream model will also be confused if you don't feed it the right data. So considering the timeline, this was something that we couldn't check yet, but actually without the player and ball coordinates, our model was also doing a very decent job. But this is something you should and must add. So let's take a look at the start of game prediction. So this video is going to show you a probability curve. I'm going to pause here. So what you see here is the probability number of the prediction based on the last 3 seconds of video that it has seen. So now it's predicting a very low number, but you will see as we're getting closer to the kickoff, it will become more confident. And I will pause it here. So you see at the moment of kickoff, the model is predicting 98%. So it's very confident that the start of game event has happened. If I resume, the next second, it's going to make a prediction call based on the last 3 seconds, and now it's getting a bit less confident, 82%. And if I resume again, the confidence level is gone. So it's a very narrow peak, which is good because we have a very strict timestamp on when the start of game happened, and that means in terms of our application that we can start the clock on the corner of the player so that the end user knows the game has started and this is the time the video has been going on, or the game has started. Then for goals, this was actually the most complex one. So I already showed you the start of game, and we kind of noticed that the start of game was also predicting goals. Why? There's an obvious reason, because you have a kickoff after every goal. So we also noticed that that model was also doing a fine job of predicting goals. The downside of this is that it has a delay, right? Because the kickoff after a goal only happens after 30 to 60 seconds. So this could be kind of not acceptable for business if it's really that strict of a requirement. So we experimented with a lot of different models, but we did not succeed yet to defeat the start of game model. So we experimented with a lot of things. One of the things was also sound, but the sound was too noisy to be a stable feature. Sometimes the audio encoder was at the other side of the field, sometimes it was right above the cafeteria, so it was not stable enough to get our confidence level up. Okay, so this was the first part, which was covering a lot of data and machine learning models. Now I will talk to you about how we actually use those models in a backend system to actually crunch through the data within 10 to 20 seconds. And we're going to dive into some code as well. So first I'm going to present you the high-level solution architecture. So going from left to right, first we need to transform the video stream into frames, because we need frames to make sense out of the data. Our models are expecting frames as input. So this is the first step where we are manipulating the data. We are going from streaming feeds to frames. Then we will send the frames over to a message queue, which is, in our case, Google Cloud Bigtable, but this is managed Kafka. Once the frames are on the message queue, they are waiting for a data processing engine to be processed. And in this case, we are working with Apache Beam, and it's running on Google Cloud Dataflow. But I will cover this more in detail. If you don't know about Apache Beam, I will slightly cover it right after. So the data processing is happening on Google Cloud Dataflow, basically with the Apache Beam model. And we are getting our predictions from our models via TF serving. Those models are hosted on Kubernetes engine. And this is kind of way how we communicate with our models. So we can get predictions for every frame or every window that we are processing. Once we have all of the predictions, we dump those predictions to, in this case, Google Bigtable, which is managed HBase. And then we have a player, a client player on Kubernetes, which is going to visualize all of the predictions, and it's basically sitting on top of those Bigtable predictions, just to visualize what we just predicted. But I'm also going to show this later on. So just very briefly about Apache Beam for people who don't know it yet. It's a programming model to unify batch and streaming. So the very nice feature of it is that you can use the same code to do batch processing and to do stream processing. So this is a very powerful feature. And you can define your pipeline in the language that you choose. So it can be Java, it can be Python, it can be Go. There are several languages available. You define your model, your pipeline basically, and then you can execute that onto many different runners. And here I've tried to list up the main runners. So you have like Spark, you have Flink, but in our case we used Google Cloud Dataflow because in this case we are using managed services. We don't need to bother anything about the underlying infrastructure. It just acts serverlessly for us. So let's get back to the problem landscape and now turn it into a solution landscape. So going from left to right again, so the video feed is on an URL in the cloud. We take that in our transcoder, we chop it into frames. We push those frames onto a message queue. Then our pipeline or processing pipeline will take in those frames, process them, call our models on TF serving to get predictions. And then once that's done, it will dump the predictions to Bigtable to store all of those probabilities. And then we have a player which is sitting on top of those predictions to visualize them and to make the game available in an enjoyable way. Okay, so now I'm going to zoom in on the biggest or most important pieces of the solution, and I'm also going to go into some code. So first of all, I want to talk about the transcoder. So yeah, we are machine learning engineers, so we kind of always or most often work with Python. So there's a lot of Python code snippets in here. Don't be afraid. It's kind of okay and very easy to read. So the things we used for the transcoder is we need to go from HLS, which is HTTP live streaming, and we need to go to JPEG to frames. So what we use for this is we use the FFmpeg package, which is a very known library to do video transformations, and we used it together with async.io to do some asynchronous processing to publish into PubSub to our message queue. So let's get into some code, right? So first what you have to do for the FFmpeg is we need to define a process, and it will basically take in the URL, and it will start to produce frames, and it will drop it into standard output. So just have a look at the parameters which we are passing to this process. Is the URL. We're saying, please take in this, or please process this video feed. Please chop it into 10 frames per second for us, and drop it in the standard output. And very importantly, run asynchronously. So that means whenever it drops a frame to the standard output, it will go back and already process the next one. So it will not wait until the downstream process to start producing the next frame. So downstream, we define another asynchronous function, which picks up the frames from the FFmpeg process, and then we'll publish them onto the message queue. So here, just looking at the code, so it will just loop over the standard output, and then for every hit it gets, for every frame it gets, it will manipulate those bytes and transform it into a base64 encoded string, and then we're going to publish that frame onto PubSub. So very easily readable code, but there's one thing which I've hidden for now for you. We also need to publish the time. So I'm going to go quickly back to the previous one. So what we're publishing to our message queue is just the data, the frame. The topic, of course, we need to know where we need to, which is our message queue. So that's not inside of the message itself, but we're posting the data and a game ID, because, of course, downstream, our pipeline needs to know to which game does this frame belong to. But in order to do windowing, we also need to know the event timestamp. When did this frame occur in the game? And how can I sort it or window it into the right order? That's the question we need to solve, right? So this piece of code, which is highlighted here, will add a timestamp, and will also publish that timestamp together with the frame. So downstream, we can know where to position this frame. And there's a kind of trick we played on Dataflow here. We used a timestamp in the future. I can explain why. So in Dataflow, or Apache Beam, has a concept which is called watermark. And watermark will try to keep track, or will try to keep a relationship between event time and processing time. It will basically try to predict when it will have seen all of the data, and basically discard all of the data that comes after. But in our case, we know, so this is very helpful in like other applications which are handling with social media and so on, where you don't know what volume will come in. But in our case, we know exactly how many data we have to process. We know the length of the game. We know the frames per second, so we know exactly what we need to process. So that's why we will not work with the watermark, but we will just go around it. But I will come back to this later on when we go into the pipeline. You will see how it fits with that. So now that we have our two processes defined, we just need to chain them together. So what we're doing here is we're defining an asynchronous loop, and then we're just going to say the stream frames to PubSub, and it plugs in on the FFmpeg process. So the FFmpeg process will continuously drop frames in the standard output, and then the asynchronous downstream function will pick up that bytes string and then publish that to PubSub. Okay. Okay, so the next part is the biggest part actually of the backend system, which is the actual processing and the communication with our machine learning models. So getting predictions from machine learning models, as I already said, we are using Kubernetes to host our models with TensorFlow serving. And why did we go for Kubernetes? Because we can use different node pools on Kubernetes, because our models also have different specifications. So remember, we have a model for detecting players, we have a model for detecting balls, we have a model for predicting start of game, and these models all have a different architecture in terms of neural networks. So they can be very large, they can be very dense, and they all have their own specifications in terms of how many compute power they need. So for some you will need GPUs, for others not. So you want to have this flexibility in machine types. And this is why we went for Kubernetes. And one very handy trick in Google Cloud is that you can just open up an internal load balancer, which means that that IP is addressable from within your virtual network, but not outside of it. Because we need to ping those, or we need to communicate with those models from Dataflow, but we don't want to go over the outside internet. So that's a very neat way to communicate within your virtual network. Then the processing of the frames happens in Beam. So Beam will window the frames that come in out of order. So just as a refresh, so message queues, Kafka or Google Cloud PubSub, it comes in out of order, but of course you need to window them and you need to sort them. So that's the job of Apache Beam. And Beam has auto-scaling, so it will start to scale whatever it detects higher workloads coming in. So just imagine, again, 3 p.m. in the afternoon, a lot of games will start up, and Beam will also scale along. We used Kubernetes and TensorFlow serving and not AI Platform, because AI Platform is a managed service of Google Cloud to do this kind of job for you, to manage the infrastructure for you, for scaling. But at that point in time, there was no support yet for GPUs, and there were also restrictions on traffic, which we were exceeding. I'm also saying at that point in time because this was half a year ago, so by now the specs has changed and this can be outdated. And then we used Beam to do the processing of the video frames because it comes along with the windowing functionality. And also, of course, the serverless scaling, but mainly the windowing is a feature that you can write as a developer with just a few lines of code, but imagine that you have to do this yourself. For example, in Kubernetes, this would introduce a lot of complexity. So by just using these managed services, it allows us to really fast develop a solution, a product. So let's have a look at what the player looked like. So this is the kind of visualization that you've seen before, which is not really enjoyable to watch. So what we will do is we will zoom in where the action is happening, and that's because we know the player and ball coordinates. We know where the action is happening, so we can pane in on where the action is happening. And here we're also turning on the team detection just to show you that this is the underlying data by which we can zoom in. You also saw the minimap as well, and on the left top corner you also have the time of the game and so on. So, oh, sorry. We'll play it one more time. Just so again here zooming in, because we know the player and ball coordinates, we can make it more attractive to watch. And just also to showcase the player and ball tracking with team detection, which is underlyingly to the zooming. The minimap, it can be sometimes jumpy, but that can be smoothened. Just imagine if we had multiple cameras, data would be much more stable. Okay, I'm gonna go back. So now I'm going to zoom in on the Google Cloud Dataflow or the Beam pipeline itself. And first I'm going to walk you through the functional steps of the pipeline, and then I'm going to take you through pieces of the code. So from left to, so all of the rectangular boxes are processing steps, and whatever is between those boxes are the data format that's being interchanged. So going from left to right, the first step that we need to do in this pipeline is read from PubSub. So this will just take in the data from PubSub. We're passing on a PubSub message instance to the next step, which is the pre-processing step. The pre-processing step is cropping the images, so they are digestible for our machine learning model. So it's kind of doing rescaling, cropping, and then we're passing this on to the prediction step, which is the third step from the left. So then we're going to make a call to Kubernetes, to our model, to get player and bounding boxes, and also do the team detection. And once we have the general information on a frame-by-frame basis, we're going to start with windowing. So then on the right-hand side, you see that there's multiple streams, each a single stream per event. So the top one is start of game, the second one is goal, and you can go on for fouls and so on and so on. And the very important thing that you need to see on this slide is that although on the left-hand side we are doing processing for one frame only, on the right-hand side we have flexibility to window frames into multiple windows. So just assume that your start of game model needs windows of 3 seconds every single second, but your goal model, your goal machine learning model, actually needs more data. It needs 10 seconds to be able to confidently predict whether a goal has happened. So then you can just use the windowing functionality of Beam to window those frames into multiple downstream windows, which is a very powerful trick to have as a developer. So I'm going to pick a single stream, the start of game. So what we'll do is we'll assign a window to the frames. We'll say that we want windows of 3 seconds every single second for our model. The next step is adding the window time to the key. And this is a kind of, not cheating, but playing along with the games of Beam, that the key is the unit of parallelism. So what would happen if we just use the game ID as key of the element that we're passing along? So you see there's a tuple, game ID, and then the frame. If we just work with this, what happens with Beam, if we window and then process downstream, it will put all of the data per key on a single machine. That means, in this case, if we don't add the window time, all of the windows for a single game would end up on one single worker, which is terrible because that's actually where we want to use Beam to do the parallelization downstream, because that's actually heavy lifting, the processing of the start of game. So that's where we want to parallelize. So that's why we're adding the window time to the key to make sure that it's unique, and then Dataflow will spread the workload out to multiple workers. Then after adding the window time to the key, we will group by key. So that's where we actually materialize the window. So you can see before this step, it's just a frame without a list. But after the group by key, we're actually materializing all of the frames for that given window. And then the pre-processing step afterwards is about sorting them, right? Because just by grouping them, it doesn't mean that they're in order, and our machine learning model needs to have frames that are in order, right? Because it will not make sense to give it data in an unordered way. Okay, so this is the pre-processing step, and then once we have pre-processed the window data, we can pass it on to our model, which is expecting the data that we are supplying it. So we're going to make a call to our start of game model on Kubernetes, and it will give us a prediction, 80%, 98%, 0%. You've seen it before. And this kind of thing is happening for every single event. So I've just talked you through the start of game event, but for the goal, it will be quite similar, but maybe with different window sizes, depending on what kind of data your model is expecting. Okay, so now I'm going to talk to you or walk you through some of the codes, which I just explained on a functional level. So how does Beam work? So first you need to define some options for your pipeline. So in our case, we use Google Cloud Dataflow Runner. So we need to specify a Google Cloud project. We need to specify a name and then a range of workers to how many machines can it scale up, the disk size, and then just a flag streaming true. And this is just how easy it is to switch between batch and streaming. So it's very nice to see that this is just a toggle that you just flag yes, true or false. So once we've defined the options, we can construct the pipeline, and then we can start attaching steps to it. So the first thing we need to do is we need to read frames from our message queue from PubSub. So this first function is, as you can see, beam.io.read from PubSub. So Beam has built-in IOs for many different kinds of data sources. So it can be a message queue, it can be a database. In this case, it's a message queue, and it's read from PubSub. So we just need to define the subscription. So where is the data at, which message queue? And then we're going to say with attributes yes, because remember that we also need to get the game ID and also the timestamp next to just the raw data of the frame. So that's why we're saying, yes, please also get the attributes of the message, and the timestamp attribute is timestamp. This is the key of the attribute that's going to be the timestamp. This is very important because that's how Dataflow or Beam will know where to position this frame. Was it here we will tell it this is the 3-minute frame, 3 minutes and 100 milliseconds, etc., etc. So this is how Beam can know the windowing, how it can relate to that. So the next step is pre-processing. So as I told you before, the pre-processing is about making crops. So as you can see, out of the frames, we will do a function which is create crops, and basically it's just gonna divide the frame into 5 crops, because our model is expecting the specifications of a crop, which is a lot smaller than the wide video feed that you've seen. So that's just, we're gonna make crops out of it and pass on a tuple to the downstream function. You can see here at the bottom, we're just gonna return a tuple with the game ID and then the frame information, which is just a dictionary, all of the information of the frame. So once we have the crops, we can start getting predictions. can start getting player and ball bounding boxes. So here, the next two steps in our pipeline will be getting bounding box predictions and getting for players and for balls. And you can see that we need to pass along the URL. So this is the IP address and of course the path where our model can be requested. So here we're passing along the URL where we can ping our model to get predictions. And underlyingly, these two methods are of course doing the kind of same thing. They will just loop over the crops, put them in a request, and then just ask the response from our TF serving. And this is how we integrate how we integrate model serving with data processing in our case. So once we have all of the bounding boxes and for the balls and players, we need to also transform them. Remember that the field is warped, so we need to dewarp it. So this is a next step in our pipeline. We will transform them. Why is there a mapping URL in one of the parameters? This is because for the dewarping, you need to know the corner points of the field. And the mapping is just keeping track of this field ID. The corner points are at those locations. So if we know the corner points, we can do the dewarping, and we can eventually get to normalized field coordinates for players and balls. Once we have done that, we can do team detection. So if we know all of the field coordinates, we can cluster them based on color, as I told before. And then now that we have this data of bounding boxes and field coordinates, we can start dumping it to our database, which is Bigtable in our case. So the first thing we will do is do a formatting of the data. Why? Because we want to keep track of these predictions are coming from which model and from which version. Because during the development process, you will also try out new models, new versions of models, and you kind of want to compare them after each run. So that's why we have a formatting step, just to add also the name of the model which we use to train it, and also the version. And then once this is done, the formatting is done, we can just dump that data into Bigtable. And we're just going to reference some of the database specs to know where it has to write to. That's the second step. So then, this was the first part of the pipeline. Remember the general stuff, which we do on a frame-by-frame basis. But then we need to start windowing per event. And this is, again, the start of game example, which I'm going to cover. So what we're going to tell here is that we're going to start windowing all of the bounding boxes, so the former data object that we handled. And now we want to start windowing them. And we're going to say, window them, please, with the window size of the start of game model. So SOG is abbreviation for start of game. And we're going to say, please window it into 3-second interval, a 3-second size with an interval of 1 second. Okay, and then there's a trigger. So what does this trigger mean? Is we're going to say, okay, whenever you've seen 30 elements for a window, you can fire it. You don't need to wait for other data to come in. You can just fire it after 30 elements. Why is that? Because, as I've told before, we know exactly how much data will come in, right? 10 frames per second, 3 seconds, that means 30 frames. So that's why we can avoid the watermark from Dataflow. We don't need that complexity because we exactly know how many data elements that will come in. So that's why the trigger is there. And that's also why we kind of manipulated the timestamp in the futures, just to make sure that Beam would not discard the data. Then the next thing is adding the key, adding the time of the window into the key, just to make sure that Beam does not put all of the windows on the same machine, right? Because key is the unit of parallelism in Beam model, so you need to make sure that your keys are well spread or well defined. So in this function or in this class, we're just going to add the window time into the key. We're just going to slice it into the first element of our tuple, so it gets unique, and then this will make sure that downstream all of the start of game predictions will happen on different machines. So it will not execute them sequentially, because that would cause a very high delay for the end users, and that's something we don't want. So we need to add it into our window, add it into our key, so it gets distributed very well. So once we add the window time into our key, we can then materialize the window by the group by key action, which is happening there. And then once we have our list of frames, we can start doing the predictions for our start of game. So here we're doing again 2 steps. Filter element is just going to throw away data that it doesn't need, just to make it a bit more light. And then the second step will be to get the start of game prediction. And here we're passing on 2 URLs. So the inception model where it can be reached, and also the start of game model where it can be reached. And then underlyingly, you can see this is how the request gets formulated to our machine learning model for start of game. So it will take in 2 feature sets. One is just the inception, so the frames RGB, and the other one is the optical flow. So it will take in 2 lists of those feature sets and try to make sense and get to a prediction. Once we have those predictions as well from our start of game model, we again will dump all of the data to Bigtable so our player can use that data to visualize it. So again, here 2 steps. Formatting. So again, we want to keep track of which model did we predict it with and what was the version of the model. So these metadata is very important to compare models afterwards. And then the second step is just to write it to the database. So this story goes on for all of the other events, right? This was just the start of game event as an example. I just want to also discuss what were the challenges that we faced with this approach. And one of the things was auto-scaling, because it's kind of linked with the auto-scaling of Beam. So our processing pipeline will scale, but then also our models will get more calls and they also need to scale. So that was kind of hard. And why? Because you might know if you work a lot with the cloud that sometimes getting a node from a cloud provider can take some time. But when you need to attach GPUs to it, it takes longer, right? So if you just look at this visualization, so we have a constant demand, right? We know how many frames that will come in, how many games. But what Dataflow will do is it will, or what Kubernetes autoscaling will do is it will start detecting this higher demand, and it will notice that it needs to scale. But of course, you need to get your nodes from your cloud provider. You need to attach GPUs to it. So it will need to overcompensate to make up for all of the requests that are waiting in the backlog. And that's exactly what we don't want to happen, because we have a latency requirement. So we don't want this backlog to be piling up. We actually want to have a stable latency. So that's why in our case, we just monitored the amount of GPUs and nodes, because we knew exactly how many games were starting. So we kind of did this monitored wise, I would say, and not relying on the autoscaling of Kubernetes based on CPU. So I've touched upon some of the components in the architecture, but one thing I would also like to mention is how do you get there? Because this is what you draw at first, and this is how it will work, but how do you get there? Because in the beginning you don't have the transcoder available, but you want to start working on the pipeline. So it's kind of hard because you have a lot of different tracks and it all needs to come together. So I'm just going to explain some tricks that we use to speed up this development process. So as I said before, Beam, it allows you to develop the same way, and you can use the same code for streaming and batch. So for us, the transcoder at first was not available. So that means that streaming data was not really feasible at first. So what we did with the Beam framework is we could just work with batch data, right? We just have some frames stored on a cloud bucket, and we just pull those in for our pipeline. It's just changing a simple source in Beam code, which is very helpful. So once we use this, we leverage this batch data to get more confident in our pipeline, how it's working, how it's processing the data. We can start testing also in streaming mode. So we just take some frames from a cloud bucket, put them on PubSub, on Kafka, and then just see how our code responds to it, just to quickly check whether the batch and streaming alignment is still valuable. And then after you're, let's say, more confident and the transcoder is also being built, then you can start putting all of the things together. So I'm going to explain this from left to right. So there's a schedule API, which a microservice, which is called the fetcher, will fetch from time to time, and it will tell when a game will start. And when it fetches that a new game will start, it will pass on a message to another microservice on Kubernetes, an orchestrator, and this one will launch a transcoder job for the game that it has just received its information for, and it's going to provide the URL and the game ID to a transcoder service job, and that will be set up for that specific game. In parallel, it will also resize the GPUs or the node pools for our models, so the models, specifications, and infrastructure is in line with how many games we have running. And the nice thing about this setup is that just imagine more and more games starting, so more and more transcoders will be piling up, but also our streaming pipeline will scale accordingly, thanks to the Google Cloud Dataflow managed service. And then downstream, of course, we have storing all of the frame probabilities, and we visualize that in a player. One more thing is that you cannot just visualize probabilities, because your models, start of game, you will predict, as you've seen before, 98%, 82%, but you will not report 2 start of games in 2 sequential seconds. The same thing holds for a goal. You might predict a goal for 5 seconds long, but you need to put some business logic on top of this. So just that a goal can only occur once every 2 minutes. A start of game can only occur once. So there is some kind of post-processing going on top of those probabilities to actually classify events. And that's also being passed on to the player. All right, thank you for attending this session. I hope you enjoyed it. I'm happy to, I see the time is up, so I'm happy to take any questions here at the booth so the next speaker can get ready. Yeah, thank you for watching this.